Hello and welcome to Kognito Key. Today, we're going to pull back the curtain on a little piece of everyday magic. You know, how the sound of your voice, which is a smooth analog wave, gets perfectly translated into the sharp digital language of computers? Let's jump right in. Have you ever just stopped and thought about it during a phone call? How does your voice travel across these massive digital networks and come out crystal clear on the other side? I mean, how does something so continuous become something countable, something digital?
Well, the secret is this absolutely brilliant process that acts kind of like a universal translator between the analog and digital worlds. It's called Pulse Code Modulation, or PCM for short. And honestly, it's the unsung hero behind pretty much every digital conversation you've ever had. So let's see how it works.
All right, so first things first, what exactly is pulse code modulation? To really get it, we need to start at the very beginning of the journey. So, at its heart, PCM is the go-to method for taking an analog signal, like your voice or maybe music from a guitar, and turning it into a digital format. It's this digital code that can be sent super cleanly and reliably across a network without getting all distorted. You can think of these PCM systems as waveform coders. Their whole job, their entire purpose, is to take a smooth, flowing wave and represent it using the simplest language computers understand, a long string of binary pulses, just zeros and ones. It's a total digital makeover.
Okay, so how does this digital makeover actually happen? Well, it all kicks off inside what we call the PCM transmitter. This is where a really cool three-step transformation takes place.
The whole process boils down to three crucial steps: sampling, quantizing, and encoding. Imagine it's like a little factory assembly line that takes that smooth analog wave and rebuilds it, piece by piece, into a stream of digital data. Let's break down each one.
First up, we have sampling. Okay, imagine taking thousands of super fast snapshots of the sound wave every single second. Each one of these little snapshots, or samples, captures the exact height of the wave at that precise moment. Now, there's a really important rule here. You have to take these samples at least twice as fast as the highest frequency in the sound. If you go any slower, you'll miss the details and the sound just won't be right. It's a fundamental rule called the sampling theorem.
Right, next up is quantizing. So the samples we just took could have like an infinite number of different values. Computers really don't like infinity, so to make things manageable, we round each sample's value to the nearest level on a preset scale. It's a bit like measuring your height to the nearest inch instead of using endless decimals. Of course, this rounding process isn't absolutely perfect. There's always a tiny bit of imprecision. And that small gap between the original sample and its new rounded value, that's called quantization error. It's basically a tiny bit of noise, like a very faint hiss that gets added to the signal. And what's interesting is you're more likely to notice it when things are quiet. And the final step on the assembly line is encoding. This is where each of those clean, discrete levels from the quantizer gets its own unique binary code. So, level 5 might become 0101, and level 10 could be 1010. And just like that, boom, our analog wave has been completely translated into a digital stream of zeros and ones, all ready for its big journey. But sending that signal out into the world isn't so simple. The transmission path out there is full of noise and interference that can mess with our perfect digital signal. So how does it even survive the trip?
See, as these little binary pulses travel, whether it's down a wire or through the air, they can get distorted. A nice sharp 1 might get all rounded and weak, and a clean 0 might get a bit fuzzy with noise. And over a long distance, this can get so bad that the signal becomes completely unreadable.
But this is where the hero of our story makes its entrance, the regenerative repeater. We place these incredible devices all along the transmission path, specifically to fight back against all that noise. And they don't just boost a weak signal. Oh no, they completely rebuild it from scratch.
So how does this little hero work its magic? Well, first, it reshapes the messy pulse to give it back its proper form. Then, it gets the timing just right, locking onto the rhythm of the data. And finally, the decision-maker part looks at that ugly, noisy pulse and makes a choice. Is this a 0 or a 1? It then generates a brand new, perfect, clean copy to send on its way. This is the superpower of digital. You can just regenerate the signal perfectly, over and over. It's PCM's greatest strength for sure.
Okay, so our signal has survived its tough journey. Let's move to the final stage, the receiver. It's time to turn this stream of numbers back into the original analog sound. So the receiver's job is actually pretty simple to understand. It just does the exact opposite of what the transmitter did. It takes that stream of zeros and ones and carefully rebuilds the smooth, continuous wave that we started with.
And this reverse makeover also happens in a few stages. First, we clean up any last-minute noise. Then, a decoder, which you might know as a DAC or digital-to-analog converter, reads all those binary codes and turns them back into voltage levels. And finally, a special filter smooths out the blocky steps between those levels, basically connecting the dots to flawlessly rebuild the original sound.
So now that we've seen the whole process from start to finish, it's pretty clear that PCM is a seriously powerful technology. But like with anything in engineering, it's not all sunshine and roses. It comes with its own set of trade-offs.
On the one hand, the biggest advantage is that PCM is incredibly immune to noise, and that's all thanks to our heroes, the regenerative repeaters. It also lets us send data securely, but there's no such thing as a free lunch, right? The price you pay for all that quality is bandwidth, a lot of it. Plus, the whole system is pretty complex, so you need some smart hardware at both ends.
And that really brings us to the main trade-off. It all comes down to quality versus cost. If you want higher quality sound, you need more levels in your quantizer for a more accurate measurement. And to get more levels, you have to use more binary bits for every single sample. It's a straight line. More bits means better quality.
But here's the catch. The more bits you use per sample, the more data you're trying to send every second. And that means you need a much bigger digital pipe or bandwidth to carry it all. So higher quality sound demands a wider digital highway. That is the fundamental compromise at the very heart of PCM.
You know, PCM truly revolutionized how we communicate. It literally laid the foundation for the clear, digital world we all live in today. It makes you wonder, right? What's the next great barrier for us to break? What's the next big challenge in our quest for perfect communication?
Hey, if you enjoyed this journey from the analog world to the digital one, please show us some love with a like and share this explainer with anyone else who's curious. And to keep decoding the amazing tech that shapes our world, make sure you subscribe to Kognito Key. Thanks so much for watching.